In today's separations class, we're going to finish discussions of countercurrent liquid-liquid extraction by talking about the three types of problems you may be asked to solve about these systems. Same type of problems that we've covered for distillation and for absorption and stripping, just applying them to the new situation. So taking the same problem that we had from last time, I wanted to highlight the fact that originally this was a design type problem. And what makes it a design type problem is the fact that we had to calculate the number of stages. N stages is the main variable. And the given information that we had was that the solvent flow rate is 200 kilograms per hour. It was 100% vinyl acetate. And we had a composition given for our last raffinate was 0.05 acetic acid. These pieces of information given in the problem statement, classify the problem as a design type problem. And last time I talked about how to solve the problem graphically, and you may have found that it was a little bit more conceptually difficult to understand, but mechanically it was quite easy because there were no calculations that we had to do in order to find the number of stages. So just real quick to recap the process, the solvent point is given, the feed point is given. We know the relative amounts that they are mixed together, so we can find the overall mixing point. And then we know where the composition of the last raffinate is, and the last raffinate and the mixing point has to be collinear with the first extract stream because of an overall material balance. And then we said we found the delta point. So delta is a point common to all streams. You can say it's R of stage n minus E of stage n plus 1 is equal to delta. And the fact that this is a generalized formula just for any old stage n means that delta is a point common to all points. So by connecting the feed point to E1, remember feed is like R0, and by tracing that line all the way over to the left, and then by figuring out where Rn and S are on a line, and remember S is kind of like E of big N plus 1, and N happened to be 4 here, so E5. Tracing that line all the way out, finding that intersection point gave us the delta point. And then from there, we know that E1 and R1 are in equilibrium because they both come off of stage 1, so they're connected with the red tie line. R1 is connected with delta, where it crosses the equilibrium curve is E2, and then the whole process starts over again. You keep stepping stages until you get to your specified Rn. Now what the problem didn't ask, and what it could ask me to do, is what are the flow rates of all these streams? We did not calculate that just yet. So to do that, we could easily read the compositions off the diagram, but in order to figure out the flow rates, we need to do a material balance. So I'm going to draw myself a process flow diagram, pause the video really quick, and I suggest you do the same. Just get yourself a 4-stage process flow diagram. All right, so here's the process flow diagram. This is not new information. This is all taken from last time, so go back and look at your notes if any of this looks unfamiliar. Importantly, note that F minus E1 is negative 136, and similarly, Rn minus S is 64 minus 200, also minus 136. That is because 136 is equal to the delta point, and that will be the difference between any pair of crossing streams in this process flow diagram. Therefore, if I want to figure out what R1 and E2 are, I know that the difference between them has to similarly be 136 kilograms per hour. That is my implied unit in all these numbers, even though I'm not writing it every time. So just like I did for the mixing point, what I can do here is I can go through and figure out what the composition of the mixing point is by doing a material balance on the 3 components. So I'm going to go ahead and do that. Go ahead and see if you can do the material balance and figure out what the composition of this delta point is. All right, so this is the generalized material balance. Oh, just realized I made a mistake. It's supposed to be minus there, but other than that, looks okay. We can use this generalized material balance to find all three compositions. So let's just go ahead and, well, obviously rearranging it, just bring the delta over to the other side. So therefore, let's do X acetic acid at the delta point and figure out what that is equal to. Let's see, Rn. So I'll just do, I can evaluate any pair of crossing streams, and because the delta point is the same, no matter what stage, it shouldn't matter what stage I do. So stage one looks pretty easy, and then I'll check myself with the last pair of crossing streams at the very end. So composition of acetic acid in R0. So we're evaluating for little n is equal to 0, in other words, the feed. So it's 100 times 30% minus 236 times 12%, all divided by minus 136. So calculate that number, and I get negative 0.012. And looking at the diagram, you may think, well, that doesn't make sense because the composition can't be negative. But remember, the delta point is outside the regular triangle, so it's not a big problem. And just imagine that I had the entire plot space filled up, not just this triangle. And remembering that the acetic acid is the horizontal lines, you might say that this delta point is just a little bit below 0% acetic acid. So in other words, this does make a lot of sense. Continue to do this. Let's find the other two compositions. And we'll check ourselves similarly, just looking to see that it logically looks to be in the same place. Let's try water at the delta point. So it's 100 times 0.70 minus 236 times 0.04, all divided by minus 136. Another calculation. And that number worked out to be negative 0.445, which again looks bizarre because it's negative, but if you look at where the actual point is and then try to map it onto where that water composition is, remember there are lines that look like this, and now I'm evaluating tick marks like that into the negative space of water, it makes sense that it's that low. So at this point, I could continue going on and do the vinyl acetate balance, or I could use the physical constraint, which does still apply. And actually, I think I'm going to show it to you just in case. X vinyl acetate of the delta point would be, there is no vinyl acetate in the feed, but there is 84% vinyl acetate, so minus 236 times 0.84. all divided by minus 136. Calculate again, and it gives me 1.46, which again is not possible because it's above 1, but it would be a line like this, remember, because those are the vinyl acetate lines, and it is above 100% vinyl acetate. So again, the physical constraint still holds. The sum of these do add up to 1. Now I want to just check myself. I said I was going to check by looking at the last stage. So let's just check that for X vinyl acetate of the delta point, but evaluated at the last stage. So this is stage 4. Let's see, vinyl acetate 100%. Oh, that's my extract. Sorry, 64 times 0.03 minus 200 divided by minus 136. That should be the same composition. And it is. It is 1.45, 1.46. So again, it doesn't matter which stage or which pair of crossing streams you use, they should all be the same. Now you may be asking yourself, well, how does that help us? How do I get to figuring out what E2 and R1 are? Well, the composition of this point can then be used in a material balance to find what those compositions are. So give me a second, I'm going to erase and see if you can derive the equations for yourself. All right, so we want to find the flow rates of E2 and R1. So I'm going to do that with the two material balances like I've been doing. I'm going to say R1 minus E2 is minus 136 because it has to be equal to delta. And then I'm going to pick a component to do my other balance. So I've got two unknowns in this equation, which means I need one more equation to solve. And I'm going to refrain from choosing acetic acid as the component that I balance for the reasons that I stated in an earlier video, which is that the compositions will be quite similar to each other. So I'm going to pick, let's pick water. So I'd look at R1, so let's look at the composition of what R1 is. I've got maybe 72% water. So 0.72 times R1 minus, and E2, I have very little water, maybe say 3%. 0.03 times E2 is equal to, my water composition is negative 0.445 times delta point. And there I have two equations with two unknowns that I can go ahead and solve. So I think the video is long enough at this point. I don't have to belabor the point and go through solving for all of these. I just wanted to illustrate how you would do it. And then I'll further illustrate that you don't have to do a balance with the delta point. If I just take the compositions from E2 and R1, and I plug them into this process flow diagram, I've got two unknowns, three material balances. So I don't have to do the material balance in terms of delta. I can just say, I can do the old material balance and say R1 minus E2 is equal to F minus E1. And then similarly, I can say it's X water in the feed times feed minus X water in E1 times big E1. So the pick your preference, typically the delta point is a little bit simpler because there's one term as opposed to two. Now, why do I go through the trouble of showing you all these calculations? And it is because I made a point to say last time that you could solve the problem of a design problem by just drawing lines on a graph. But I've been saying all semester that that is not a very good way to learn the material. Like, sure, you can memorize the steps and know you can go through algorithmically, you draw a line from here to here and you step through and solve the problem. But it does a very poor job of teaching you what's actually going on. So by doing these material balances in a little bit more detail, hopefully it gives you a little bit more context of what actually is meant when you draw a line between 2 points and you solve the problem graphically. All right, so that's it for this video. I got two more videos with the other two types of design problems.